using the first derivative test that we're studying in section 4.3 here today. And what we need to do is first of all find the derivative, then we need to factor, if possible, and do sign analysis, and find intervals of increase and decrease, and then we need to examine what's happening there. Does it go from positive to 0 to negative? That's going to be a local max. If it goes from negative to 0 to positive, that's a local min. So let's first take the derivative here. And that's going to be 4x cubed minus 12x squared minus 16x. All right? So if we're going to let this equal to 0 to find the critical numbers, that'd be a good idea. I can also take a 4 out, right? 4x. So let's just do this. And obviously we can't just remove it. We need to take it as a factor, but that's going to make things quite a bit easier for us. What's that going to be? 3x, and that's going to be minus 4. I don't know, was this a question you guys have done already? Was it? On one of your assignments? Could be. Or an example. It looks like it's an example, but anyways, okay, so can we factor this? Yep. X what? Negative 4 plus 1? All right, very good. Okay, so where this equals 0, the critical numbers. Now we can do all of this at once if we want. Did you guys do this one already? Did you do this exact one? Oh, good for you. Okay, so we can find the critical numbers on our sign analysis chart here. So put your factors here, 4x, x minus 4, and x plus 1. Put those along the side. This bottom line we understand is going to be a number line. So 4x is going to be 0 at 0. So that's a critical number. 4x is going to be negative for any value less than 0. So we put negatives there and put positives beyond. First step. Do that for each of the other factors. So we're going to have 4 here is going to be 0. We're going to have negative 1. It's going to be 0. Okay. So when we let this equal 0, and again, we don't have to let that equal 0 up there. We could just say, hey, this is g of x, and go from there. But if you want to let it equal 0, you could identify your critical numbers right away. This is also known on the street as the crit pounds. The crit pounds are negative 1, 0, and 4. You guys get that, or is that like too street talk for you? The crit pounds? You know, like the number sign is like the pound sign? Crit pound. Okay, forget it. No, it's good. No, it's all right. No, yeah, it's fine. Just trust me. It's hilarious. Not crack. I'm not talking about crack. Back to the, okay. Stick to calculus. Okay. All right, so here we can see, right? So g prime of x. We're going to be able to see some interesting things here. On this interval here, less than negative 1, this is going to be negative, right? Because we have a 0 there and everything is multiplied, this whole thing is going to be 0. We have a negative times a positive. What's that going to be?
Positive.
It's positive. This is 0. This is negative. That's 0. And all 3 positives multiplied together be positive. So, right away we can see we have some interesting things happening. We can see that from negative infinity to negative 1, the function is decreasing the whole time. Right? So it's kind of like coming down, and then it's reaching a bottom point. How do I know that? Because it changes, the sign changes from negative here to positive. See that? And then the sign of the derivative changes from positive, goes through 0 to negative. So that's going to be a local max. See that? And then it goes from negative to 0 to positive. And then it continues this way. So this is just a rough sketch of what the function might look like. We don't know how high it rises or how low it rises, but we know where the minimums and maximums are going to be. Okay? The locals. So we can say that we have, so g of x, not g prime, but now g of x has a local max at f of 0. And to make this complete, we should figure out what the y value is there and put everything in there. So what you'd have to do then is you'd have to go and put a 0 in for x in everywhere you see it and evaluate. So 0 minus 0 minus 0 minus 1.
Minus 1.
So it's going to be negative 1. Anywhere else that has a local max? Does not look like it. So where it's positive to 0 to negative, right? Positive to 0 to negative. So g of x then also has a local min at two places here. F of negative 1, and we'll show that, and f of 4. So as we plug those critical numbers in, we can find out the y values, and this is a good way to write where these maxes are, because you see the x value and you see the y value. So I would encourage you to write like this. You could show it as a point as well, local max at the point 0, negative 1. Please don't say local max at 0. Local max at negative 1 and 4. It's not enough information. The maximum and minimum values really are what's important here too, so go take that extra step. So just a refresher of the first derivative test. Yeah. If the slope changes from positive, goes through 0 to negative, we have a local max. If it changes from negative, goes through 0 to positive, that's a local min. And if it doesn't change, so negative through to 0 back to a negative, that's neither. Okay? And this holds true for all continuous functions. So here's a function you can practice on your own, and I'll show you the answer in a minute. So give it a chance to do each step on your own, and I'll show you my work in a minute. Okay, so this is a pretty straightforward one. Take the derivative, do sign analysis. You'll notice that there is no change. There is a 0, but there's no change. It's positive beforehand, it's positive afterwards. And so y equals x cubed, you know what that looks like. And that's a case where there technically is a derivative equals 0 at 0. But because the sign doesn't change, there's no local max for min.
Wait,
Questions about that? Yeah?
Why is it x squared? Oh, you're right.
You could split this up as 3 and x if you want.
Is there a point to splitting?
Oh, I see.
I did 3x.
That's why.
Whatever you want to do. You could do 3x and 3x, whatever's easiest. The x squared is always positive except for where it's 0.
Yeah,
And the 3 then would always be positive except
I
for
don't
it's
know, but
0.
I was thinking of like x value, not the x squared value. That's
Yeah. Yeah, you have to consider the squared there. Okay. I would like to show you just one thing as well. We don't have to do this one, but here's an example. I think I drew this example previous in the lesson here. If you have a y equals 1 over x squared, this is not a continuous function because we have an asymptote at x equals 0, right? Because x equals 0 would make this undefined. So this is not a continuous function, and here's where the first derivative test doesn't work. So if you find the derivative here of 1 over x squared, the derivative looks like this. Okay, if you do sign analysis, what you'd have to keep in mind is that you're dividing now by this. So that's why I put a little dotted line in between the factors here. This would be negative 2, and it would be divided by x cubed. So if you split those up into 3 x's, that's fine. X cubed looks like this. So technically, the derivative does go from positive, right? Then we have a critical number at 0, then it goes to negative. The reason why this isn't a local max is because it's not continuous because of that asymptote. So this would be a case where you have to be careful that it's a continuous polynomial type function with no restrictions on x. That's where we start getting into trouble. Okay, so it only works on continuous functions because this would look like it would have a local max, but because we're dividing by 0, this is actually not 0. The derivative is actually infinity there, right? Okay, so just a little note as you.
Wait, so something divided by 0 is infinity?
No, if you divide by 0, it's undefined, or it would be infinity. It wouldn't be 0. If you have a number divided by 0, it's not 0.
But so it's undefined and then infinity same thing.
So in order to confirm that you're doing the first derivative test properly and to make sure that it's continuous, if you find a c that seems to be a local max, That's when at the very end, when you go to find the actual maximum value, if you find that that C is not part of the domain of F, if it's a restricted value, then you got a problem. Then there is no max or min. So that's another way you can check, like we did up here, right? When we found the critical numbers and we determined, hey, there's local max and min, so let's find the Y values that go along with those. That was actually important. If you come across here, this does not exist, or infinity, then you're like, hey, wait a minute, what's going on? Then something's wrong. Okay, so that's another way you can ensure that you're doing this right.